So good morning, my dear students. Today we are going to solve a few numericals based on the torque experienced by a current carrying loop placed in a uniform magnetic field. Okay. So let's start the first question. A current carrying circular loop of radius r. So there is a current carrying loop is given which is having the radius r here. It is placed in a uniform magnetic field B naught. You can see the B naught is a uniform magnetic field acting in this direction. And they have clearly mentioned that the B naught is making an angle 45 degrees with x-axis. Obviously, another 45 degrees with y-axis also. Okay. The loop carries a current of 1 ampere in the direction shown. You can see the current direction, which is 1 ampere is the current passing through that. The question is, find the torque on the loop. What is that? Find the torque on the loop. And we all know about the expression for the torque. So what was the expression for the torque? So let me write here. Torque tau bar is equal to m bar cross b bar. Okay, so where m bar is the magnetic moment, and the magnetic moment is always directed in the direction of area vector. Okay, what is area vector here? So let's see. Area vector. So this is the current direction. To find the area vector, I have told area vector will be always perpendicular to the loop. Okay, perpendicular to the loop. If this is the loop, its area vector will be perpendicular to that. Okay. So this is the loop, circular loop we have. The perpendicular to the loop, area vector may be like this or maybe into the plane. So that we can find out by using right hand thumb rule. And current direction is by curl of the finger's direction, and you can see the thumb is the direction towards the magnetic moment or the area vector, you can see here. So as this is x, y, z plane, okay, so this is what the current direction and the curl of my finger's direction, and thumb is pointing in the direction of area vector. That's called magnetic moment. Understand? So the area vector is in which direction? If it is x and it is y, and you know your z-axis is in this way, yes or no? Your z-axis in this way. So your area vector was perpendicular to this, the opposite to this z-axis, yes or no? You can see, look at this area vector direction into the plane, okay? If it is x, this is y, and this is z-axis. So that means opposite to that, so that's your minus k cap direction. I'm writing the same here. Area vector is directed along minus k cap direction. Remember? Okay. Now, tau bar is equal to m bar cross b bar. So we have got m bar direction, so which is a minus k cap, and this is b bar. So b bar is magnetic field direction. You can see here. What is the magnetic vector here? This is vector. So we need to find in the vector form. They have not asked to find it in the magnitude. Okay, they asked us to find the torque on the loop. Torque on the loop. Torque is a vector quantity. In vector notation only we are going to find out. Okay, so now a bar is directed along minus k cap, and we know a b bar is equal to, let me write in the vector form. So this is b naught they told, right? So b naught bar is equal to, magnitude of this magnetic field is how much? B naught. Okay. So this B naught bar can be resolved into the two components along x-axis, along y-axis. I can write here. So B naught x into I cap plus a B naught y into j cap. So what is B naught x? Along x component it will be B naught cos theta. Along y component it is B naught sin theta. So that also you can write it. Okay. So now focus on m bar, right? So if we focus on m bar, we know m bar is equal to I a bar. Okay, m bar is equal to what? I a bar. So this I can also write I into a bar. Current is I, which is 1 ampere is given. A bar is area vector, right? Area vector is what? Magnitude is pi r square and the direction is what? Minus k cap. So this is what? Area vector. See, magnetic moment we have got. And B bar. So a B naught bar is equal to B naught x I cap. B naught x is B naught cos 45 degrees I cap plus a B naught a sine 45 degrees K cap. Is it clear? Now, so it's J cap. Right? X. Along x it's I cap, along y it is J cap. Clear? So what is this value? Let me write this value. So this B naught bar is equal to B naught cos 45. It's root 2 I cap plus, so this is B naught by root 2 J cap, because sin 45 is also 1 by root 2. Is it clear? So this is B naught bar and this is M bar. B naught bar we have and M bar also we have. So we are going to do the cross product to find the final value. What is the cross product? Tau bar is equal to M bar cross B naught bar. So let me write this. Tau bar is equal to M bar I into pi r square into minus k cap, right? So this is M bar cross B bar. What is B bar here? A B naught by root 2 I cap plus B naught by root 2 J cap. Okay. And one by one let us write. So this is I is 1. Anyway, as I is equal to 1 ampere, I am just substituted 1 here. So this is pi r square into, just a multiplication, pi r square into B naught by root 2, and these two can be applied cross product. Because this is magnitude, pi r square is magnitude, B naught by root 2 is a magnitude. We need to apply cross product only for vectors. What are the vectors here? This is minus k cap is a vector and I cap is a vector. So minus k cap cross I cap. Okay. Now plus again this one pi r square, again this one B naught by root 2, and what are the vectors here? Minus k cap and j cap here. Minus k cap and j cap. That's it. If you find the value of the cross product of these two unit vectors and value of the cross product of these two unit vectors, and you will get the answer. Okay. Is it clear? And how to find these values? And we know clearly what is that. I bar cross j bar is equal to k bar, cross product, you should recollect it. And j cap cross k cap is equal to I cap. And k cap cross I cap is equal to j cap. Okay. So now look at here. What is this? K cap cross I cap, but its minus is there. You can see here. K cap cross I cap is j cap, but it is minus here. Okay. So this will be minus k cap cross I cap is minus j cap. Okay. So I am writing the same here. So pi r square B naught by root 2, which is minus j cap. Is it okay? Minus k cap cross I cap. Generally k cap cross I cap is j cap. But here minus is given, so that's why it is minus j cap, right? Plus same pi r square B naught by root 2 into what is this? Minus k cap cross j cap. Carefully see. Generally j cap cross k cap is what? I cap. Look at here. J cap cross k cap is I cap. What we need? Reverse of it. K cap cross j cap is minus I cap. Okay. Just reverse of it is minus k cap. Minus I cap. I hope you are getting it. Now what is our required value? Minus k cap cross j cap. So here minus, if I apply it will be minus of minus plus. Okay. So here what is our answer? Minus k cap cross j cap is plus I cap. It's a plus I cap here. What you can take common? You can take common these two magnitudes. You can clearly see that these two magnitudes you can take common. Pi r square B naught by root 2 if you take common, and this is I cap minus, and this is J cap. So that's your tau bar. I hope you understood the given question. Alright. So it takes some time while solving in your original NEET exam, or maybe in your weekly test or the monthly test even. But a lot of practice makes you save your valuable time. And let's see one more question based on the torque acting on a current carrying loop. Let's start one more numerical based on the torque. A uniform magnetic field of 0.3 Tesla is established along a positive z-axis. Right? So there's no diagram is given. So we have to draw a perfect diagram for this question. And let's try to draw that. Along a positive z direction. So let me draw the graph of the diagram here. So this is z-axis. If it is z-axis and this is y-axis, I'm just imagining that. So this will be my x-axis. Both the three axes must be mutually perpendicular to each other. So along this x-axis there is a magnetic field. Along the z-axis the magnetic field is acting along the z-axis. This is a B bar. Carefully listen. A uniform magnetic field of 0.3 Tesla. So that magnetic field value is 0.3 Tesla. A rectangular coil of sides 10 centimeter and 5 centimeter. See, there is a rectangular coil of sides. You can see here, this is a rectangular coil of sides 10 centimeter and a 5 centimeter is carrying a current of 12 ampere, whatever it may be, current of 12 ampere. And from this 10 centimeter and 5 centimeter, you should understand the area is given. So area of this coil is 10 centimeter into 5 centimeter. You need to convert it to the meters. Okay, that's the next concept. So current value passing through this rectangular coil is 12 amperes. Calculate the torque. We know the concept of torque. Torque is m bar cross b bar. There is no vector concept is given here. So directly all the values are given A, right? So that's why we know the basic concept of torque, which is equal to m bar cross b bar, which is equal to nb sine theta, and this I can write the magnitude of the torque is m is NIAB sine theta. So this is the basic definition or the expression for the torque that you already know. Now, calculate the torque when it lies in YZ plane. What is meant by it here? It is a rectangular coil. When the rectangular coil lies in YZ plane, what is the torque? Right? Let's see. The first case. So we know already it is your Z-axis, Y-axis and X-axis. In YZ-axis, the rectangular coil is located. Look at here. This is the rectangular coil is located in YZ plane. So already the magnetic field is along Z-axis. It is there, magnetic field. And this is area 10 centimeter and 5 centimeter, and the current passing through that is 12 ampere. Okay, it's 12 ampere. Now, is it easy to find the torque here? It's so easy because the angle between area vector and the magnetic field is how much here? So the angle between area vector and the magnetic field is 90 degrees. Can you believe this? Magnetic field is in this direction. You can check the area vector is a perpendicular to the plane. Perpendicular to the rectangular coil, the area vector lies. And that is the same direction for magnetic moment here. What is the angle between magnetic moment and the magnetic field here? 90 degrees. Because area vector of this rectangular coil may be in this way or may be into the plane, and the magnetic field is perpendicular to this. You can check. So theta is 90, and you know tau is equal to NIAB sine theta. Sine 90 is 1. So where number of turns is 1. So tau is equal to IAB. Just substitute all the values. I you have. What is I? 12 ampere. A. What is area? I'm talking about the magnitude, right? What is the area here? 10 centimeter into 5 centimeters. What is B? B is given as, where is B? 0.3 Tesla. Understand? So let's type. So tau is equal to I, 12 into A, area, 10 centimeters, 10 into 10 raised to minus 2 meter into 5 centimeters, 5 into 10 raised to minus 2 meter. Area is done, current is done, and B is 0.3. Right? So now this tau is equal to 12 into this 0 and this point cancel and it will become 3 here. So 12 into it is 3. Okay, so this is 12 is done and this is finished and this is finished. What is left here? 5 is also left here and this 5 is finished, and 10 raised to minus 2, 10 raised to minus 2. This 10 raised to minus 4. When it comes to denominator, it will be 1, 2, 3, 4. Okay, 10 raised to 4. After 1, how many zeros? 4 zeros are here. Okay, now listen here carefully. 2 6 are 12 and 2 500s, right? No, 2 5,000s. Understand? 10,000. Then one more time. This is 5 1. This is 5,000s. Okay. And this one, 3 6 are 18 divided by 1000. This you can write it as 2 9s and 2 500s. And this will be 0.018 Newton meter. Why the Newton meter here? Torque, force into perpendicular distance. Okay, force into perpendicular distance. Clear? Force into perpendicular distance, Newton meter. So that is what the first case, torque. When the rectangular coil is placed in YZ plane, the torque is 0.018 Newton meter. Right? Clear? Now, what about the second case? And let's concentrate on the second case. Second case is XY plane. The rectangular coil is placed in XY plane. Rectangular coil is placed in XY plane. Where is XY plane? This is X and this is Y. You can see here. So the rectangular coil is placed in XY plane. Here also it is 5 centimeters and it is 10 centimeters. Clear? Now, torque is M bar cross B bar. NIAB sin theta. Concentrate on theta here. What is theta? Angle between area vector and magnetic field. Okay, I told you already, whatever may be the rectangular coil you take, its area vector is perpendicular to the plane. And this is the rectangular coil. Perpendicular to plane is the angle. So, sorry, it is how much here? 5 centimeters. Okay. So, if you take this is the rectangular coil, its area vector will be perpendicular to the plane in this way. Now, this is the plane XY plane. So, the area vector will be perpendicular to this plane. Perpendicular to XY plane is what? Z plane. Right? As area vector is perpendicular to this plane means along Z axis. So, magnetic field is also along Z axis. So, area vector is along Z axis. So, I am writing here in the second case, A bar is along Z axis and magnetic field is always along Z axis in this case. Then what is the angle between them? Angle between them is 0 degrees. Then the torque is equal to NIAB sin 0 degrees. Sin 0 is 0. And what is the torque in the second case? It's 0 Newton meter. Clear? I hope you understand the situation here. It's all about, while solving the numericals on torque, it's all about the angle between area vector and the magnetic field. That's it, right? These are the two basic numericals related to the torque. And we will be starting a topic called a moving coil galvanometer now. Moving coil galvanometer. Now the topic is moving coil galvanometer. It's moving coil galvanometer. So this is the topic, is most important for your board exams, right? And there is a little important for your numerical solving also, right? So the derivation is very important for your board exam. Let's start. So moving coil galvanometer can be represented with the short form MCG, right? In giving numericals also they will be using this. You should not get confused. Now let's start. So why this moving coil galvanometer? This is the moving coil galvanometer. It is a sensitive instrument. It's a sensitive instrument which can measure the small currents, in a circuit, of order 10 raised to minus 9 ampere. See how small it is. Up to 10 raised to minus 9 ampere current, this is the device or instrument can measure. Okay, so that is what the moving coil galvanometer. And what's the principle behind the moving coil galvanometer? We need to understand. So the principle behind the moving coil galvanometer is, we had already discussed. The last class topic is the principle of the moving coil galvanometer. What was the last session we had discussed? A rectangular coil experiences a torque when it is placed in an uniform magnetic field. Clear? A rectangular coil experiences a torque when it is placed in a uniform magnetic field. It's not like simply in a uniform magnetic field, if you place a rectangular coil, it will experience a torque. It is not like that. So through the rectangular coil, the current need to be passed, then there is a torque experiences by this particular rectangular coil, which will rotate continuously. And we have already discussed about this torque. So what is the torque experienced by the coil placed in the magnetic field? So NIAB sine theta. So what is this NIAB sine theta? N is number of turns of this rectangular coil. It's a rectangular coil. I is current passing through the rectangular coil. A is area of that rectangular coil. B is the uniform magnetic field, and theta. This is the most important part of the session. Theta. In the last class also we had discussed more about that theta. The theta is angle between these two. Carefully see. The angle between area of the coil and the magnetic field, right? What is the theta? Angle between area of the coil and the magnetic field. So in the last class I had shown you, so if this is the rectangular coil front view, okay, imagine this is your rectangular coil, the front view I am talking about only this part, right? So when it is rotated like this, see here, this is the front view of the rectangular coil I have drawn here. Okay, and a magnetic field is, imagine the front view of the rectangular coil is XY here. This is the magnetic field B bar, and A bar means area vector direction, or the magnetic moment direction is perpendicular to the plane of the coil. You can say it's A bar or M bar. In the last class we had discussed. So the angle between area vector and the magnetic field is this theta. When this theta is 0, what happens? The torque experienced by the rectangular coil is 0, because sine 0 will be 0. When it is 90 degrees, the maximum torque will be experienced. Okay, so now these two cases also you should understand. When theta is equal to 0, tau is equal to 0. When theta is 90 and tau value is maximum. So what is that maximum value? NIAB. Is clear? Everyone, I hope you're understanding the situation here. Now let's move on to the diagram of the topic, right? So what is that? Moving coil galvanometer, how it looks like. Okay, so look at here. In this case, we are going to have a cylindrical shaped soft iron core. Look at here. A cylindrical shaped soft iron core, right? It is cylindrical shaped soft iron core. I'm writing here. A soft iron core which is made in the form of a cylinder. And imagine a cylinder we have. So this is kept in this way. On the cylinder, a rectangular insulated copper wire is connected, right? Which is fixed like this, you can see. A rectangular copper insulated wire which is called a rectangular coil of n number of turns. So n is the number of turns of this coil. Okay. And this is the coil is having area A. Now, so you can see here, and this one end of the coil is connected to a spring. Okay, you can see one end of the coil is connected to a spring. It's so simple. This is a rectangular coil. A rectangular coil. Okay, a rectangular coil which is kept on the cylindrical soft iron core. A rectangular coil is having n number of turns and having area of cross section, and the coil is connected to the spring here. Now, this is the coil is placed in between the U-shaped magnet, right? In between, you can see the magnet like this. This way it is kept. What is that? Look at the interesting thing. Imagine this is a cylindrical soft iron core. There is a magnet of north pole and there is a magnet of south pole is kept here. Understand? There is a magnet of this south pole and there is a magnet of north pole is kept here. Carefully look at this. So this is what a north pole of a magnet and south pole of a magnet. So in between these two poles there is a cylindrical soft iron core on which a rectangular frame of coil which is made up of copper, insulated copper wire is fixed here. Okay, now carefully see. So I'm just looking from the top view, right? Carefully see, top view. Top view, I'm just going to show to you also. This is the top view. Understand? This is the top view. So there is, carefully see, north pole here and south pole of a bar, south pole of a magnet here, and at this point, see here, at this point, your front top view of the cylinder on which a rectangular coil is wounded on it, right? Rectangular coil, a rectangular frame is fixed on this. That will be visible. So that's a diagram I just wanted to draw for you. Look at here carefully. So there is here, let me draw here, there is a cylindrical coil. Okay, this is what the cylindrical soft iron core. On this, what happened? On this is what our number of coils. Okay. Alright. So top view of this. And this is fixed in between north pole and south pole of a magnet. Carefully look at the situation. Right? This is north pole of a magnet and this is south pole of a magnet. Is it clear? Now the front view, the top view of the same thing I had drawn here. And you know, this particular shape of this magnets will provide a radial magnetic field. What is that? Radial magnetic field. So this particular fixing arrangement will provide a radial magnetic field. What is the requirement of the radial magnetic field and what is the use of the radial magnetic field we will discuss later. Now itself. Okay. So now concentrate here. See how the magnetic field lines will be moving from north to south. I'm just drawing here. Carefully see. This is how the magnetic field lines will be moving from north to south. Okay. So this is how the magnetic field lines will be moving from north to south. And this is how the magnetic field lines will be moving from north to south. Okay. And this is how the magnetic field lines will be moving from north to south. Right? This is how the magnetic field lines are moving from north to south. Right? So this is the magnetic field lines are called radial magnetic field lines, and the field produced by this perfect shape of the magnets is called a radial magnetic field. Now, carefully see. This is what the rectangular coil, right? When a current passing through the rectangular coil, what happens? As it is kept in the uniform magnetic field, when a current passing through this rectangular coil, then the rectangular coil will deflect, yes or no. There is a torque experienced by the rectangular coil and it starts rotating. Okay. So when this rectangular coil is start rotating on this cylindrical soft iron core, look at here, when this rectangular coil is rotating on this soft cylindrical iron core, the soft cylindrical iron core is fixed. On this rectangular frame will be rotated. Okay. Initial position is like this. After some time, so the position of the rectangular frame will be like this, maybe like this. Okay. So this is after some time. And after some time, so this can be rotated in this way also. You got the point? So this rectangular frame on the cylindrical soft iron core will be rotated in this way. Okay. Now, I'm writing the same. When I is flowing through the coil, right? Torque experienced, definitely torque experienced by the coil is a deflecting torque. What is the name of it? A deflecting torque. And that is denoted with the symbol tau suffix d, deflecting torque. Right? So what is the torque expression? Torque expression is NIAB sine theta. I'm just writing the same here. So that deflecting torque is equal to NIAB sine theta. What is the angle theta here? What is theta? Theta is angle between magnetic field and area vector. Okay. So imagine the first position. This is our first position of the coil, right? So this is the magnetic field. As the coil is like this and its area vector is in this way and the magnetic field lines are moving in this direction. Look at here. This is the magnetic field lines direction and this is the plane of the coil, right? So this is the magnetic field line direction and its area vector will be like this. So area vector and the magnetic field are perpendicular to each other. So then in this case, as theta is 90 degrees, so tau deflecting torque is equal to NIAB. So this is equation 1. What is that? Equation number 1. Again, listen to me carefully. For example, after some time, the rectangular coil is shifted or rotated till this point. This is what the second, imagine it's the first case and it is the second case and it is the third case. In the second case, this is the rectangular coil position. How the rectangular coil is rotated? Like this. This is the rectangular coil. Understand? So the magnetic field is moving in this direction. The area vector of this plane of the coil is like this. The 90 degrees condition is satisfied. I hope you could recollect and you could imagine the situation what is happening over here, right? So listen to me once again. So initially this is the rectangular coil. This is the rectangular coil position. The top view is drawn here. So the magnetic field lines are moving like this, and the area vector for this plane will be perpendicular to that. See, magnetic field lines are moving like this, perpendicular to that the area vector is. Okay, so that's 90 degrees, and here also you can see the magnetic field lines are in the plane of the coil. Then the area vector will be perpendicular to the magnetic field lines, and you can see the third case also. And in the third case also, this is the plane of the coil, right? See, third case, this is the plane of the coil, this is the plane of the coil, and in the plane of the coil only the magnetic field lines are, and area vector will be perpendicular to that coil. Understand? So the radial magnetic field, what it will do, you know, it will constantly make the value of theta is 90 degrees, right? What this radial magnetic field will provide, radial magnetic field will helps to a constant theta 90 degrees. What is theta here? It is between magnetic field B bar and A bar. Okay, it will maintain a constant it will maintain a constant angle theta, which is 90 degrees between B bar and A bar, right? So that's the reason constant radial magnetic field is applied, and that's the reason why in this shape magnets have kept here. Okay, so this is what deflecting torque. Now there is a spring here if you observe carefully. When this rectangular frame is rotating, the spring will get tightened. When the spring gets tightened, and inside the spring there will be a restoring torque also will be developed, right? So as the deflecting torque here, there is a restoring torque is also developed. What is the restoring torque? So I am writing here. So restoring torque is also developed by the spring. So that's the reason when the current flow, if you stop, what happened? The rectangular coil will come back to the initial shape, initial position. Okay, as long as the current flowing through that, there will be a torque experienced by this rectangular coil. Once you switch off the current, what happens? It will come back to the initial equilibrium position. Rectangular coil will come back. So for example, this much rotation is taken place. This is the initial position. When no current is passing through the rectangular frame, and immediately this will come and occupies the original position of it. Okay, so that's called original equilibrium position of the rectangular coil. So that is what I am going to tell you, which will bring the coil back to the original equilibrium position, that the restoring torque, right? So that restoring torque can be represented with the symbol tau suffix r, restoring torque, which is equal to, remember, the restoring torque is equal to K phi. Right? What is K phi? I'll tell you now. Listen to me. Restoring torque is equal to K phi. So now what is that K? K is equal to torsion constant. What is that? Torsion constant. And this torsion constant can also be written as torque per unit twist. What is that? Torque experienced per unit twist. Per unit twist. And this is phi is the twist. This phi is a twist or angle of deflection. Angle of deflection. Angle of what? Deflection. Understand? So that phi is how much is the angle deflected. Understand? So initially, if this is what, see, initially this is the position. After some time, this is the position. You can see there is an angle between them. So that is called angle of deflection or twist. So that is phi. Okay. Now, how much is the initial deflecting torque? The same amount of torque will be produced due to the spring. Understand? So, for example, deflecting torque is a 5 Newton meter. So same amount of 5 Newton meter will be the restoring torque. Then only it is possible that after some deflection, when switched off, the current is not flowing, then definitely the rectangular coil will come back to its initial position. When deflecting torque is equal to restoring torque. So that's the reason I'm writing equation 1 is equal to equation 2. So that means deflecting torque is equal to restoring torque. So what I can write here, NIAB, which is equal to K phi. NIAB, which is equal to K phi. And from here, I can write I is equal to K by, carefully see, I is equal to K by NAB into phi, right? K, it's a constant. I told you here, torsional constant, which is torque per unit twist. And N, number of turns. A is area of the coil, B is uniform magnetic field. All these values which are in the bracket will never change. The only changing thing is this phi value. Phi is what? Deflection. The angle of deflection is changing. So I can say when this is constant, so this K by NAB is equal to constant, then what I can write, I is directly proportional to phi. I is directly proportional to phi. So the amount of current passing through the rectangular coil is directly proportional to the deflection taken by the rectangular coil. When more is the current passing through the rectangular coil, more will be the deflection we get it, right? So more is the current passing through that, more will be the deflection. So that's a concept of how to measure the sensitive current, how to measure the small currents in the given circuit by using moving coil galvanometer. How we'll be measuring? By spending a less amount of current also, there will be a deflection identified. By sending more amount of current also, there will be a more deflection will be identified, right? And listen, one important thing here. Generally, moving coil galvanometer is used to measure the small currents in the circuit, and generally you get a doubt. How we will be measuring the more currents then? The big, huge magnitude of the currents, how we can be measuring? So that also can be measured by using this galvanometer, but a simple modification need to be done. So that's called how we will be converting this moving coil galvanometer into ammeter, right? You know, ammeter is used to measure the currents in the circuit, but moving coil galvanometer is also used to measure the small currents in the circuit. If the currents are having like sufficient magnitude, then how to measure them? So they will definitely measure by using ammeter. So that ammeter is a device which has come from the conversion of moving coil galvanometer, right? By adding some more electrical components, we can convert this moving coil galvanometer into ammeter to measure the huge magnitude currents also in the circuit. Okay, is it clear? So now come back to this one. So this is the main concept of moving coil galvanometer. When less is the current, there will be a deflection identified. Okay, now there is a concept called current sensitivity. What is that? Current sensitivity, which is current sensitivity. Carefully see. So this current sensitivity is equal to deflection per unit current. Deflection per unit current. Unit current means what? 1 ampere. When 1 ampere current is passing through the rectangular coil, what is the deflection produced? The deflection produced per unit current is equal to current sensitivity of this moving coil galvanometer. So from this I can write phi by I, right? From this itself I can write phi by I. So I by phi is equal to K by NAB. So this is NAB by K. NAB by K. Okay, this is current sensitivity. And the same way, voltage sensitivity also can be identified. So what is voltage sensitivity here? So phi by, right, per unit voltage. Understand? So deflection produced by the rectangular coil in a uniform magnetic field per unit voltage. Per unit voltage. So per unit voltage, so volt can be written as I into R. Understand? V is equal to IR, right? So potential is equal to I into R. V is equal to IR. So which is equal to, so what happens? Just phi by I into 1 by R. Same thing. Just multiply with 1 by R. NAB by K. Understand? So this is voltage sensitivity is 5 by V. This is voltage sensitivity and this is current sensitivity of a moving coil galvanometer. Okay, so let's solve some numericals related to the moving coil galvanometer and torque experienced by a rectangular coil in the next class, along with conversion of this conversion of this moving coil galvanometer into ammeter and voltmeter.